Hello everyone, welcome to Recitation 6 on Mechanics and Materials 1. We have 4 questions as always, and this is the first one of them. You have a rigid lever shown in the picture here, and you apply a force at the end of it. A force is downwards that causes a clockwise rotation. With respect to point B. So this lever becomes like this basically. And then it's rigid, right? So it remains straight. The angle would be 2, so that angle that it makes is going to be 2 degrees. Under this loading, you are asked to compute strains in each of these cables. Okay, now, basically what you need to do is to draw the deformed shape of that lever, and I don't know, let's say this is that, and assuming that the angle that you have here is 2 degrees, what we want to do is to compute the strain in each of these cables. Now, the strain in each cable would be the change of length in each cable divided by the original length of that cable. So, let's say in cable AH, that's the first cable, the strain would be the change of height or change of length of that, let's call it delta A, divided by the length of AH. Now, that height, delta A, is this. We can think of the same thing here and here, so this would be delta D, this would be delta C. Then epsilon in CG would be delta C divided by LCG, and epsilon FD in the last cable on the right-hand side, it would be delta D divided by LFD. Okay, now these lengths, these two, they have the same length or the same height here, that's 300 millimeters. So this would be 300 millimeters. And AH on the left-hand side, that's 200 millimeters. So we have this. What we need to compute are essentially these deltas. Now, you compute those deltas obviously from the geometry of the problem. So if you kind of look at this triangle, you can immediately see that delta A divided by, let's say, this distance, which is 200, would be tangent of that angle that is 2 degrees, right? But also 2 degrees is such a small number, so it's, let's say, a very small angle. That means we can always approximate it with, sinus of 2 and just the same as 2 degrees itself. So again, remember, if theta is very small, or if an angle is very small, its sinus and its tangent are small too, and they are basically equal. So that we do basically that. We say delta A is simply 200 times theta itself. And theta here is this, this 2 degrees, which is, by the way, 2 times pi over 180 radian. Okay, so theta is essentially 0.0349 radian. Okay, so we insert that here. And we get delta A to be 6.981 millimeters. We play the same game for B and C, for C and D. So delta C is then the distance from B, which is 300 now, times theta. So delta C would be then 10.472 millimeters. And delta D is 500 theta times 500 times theta. That gives us 453 millimeters. Now you have everything you need. So you have delta A, you insert it here. You have AH, so you can calculate epsilon AH. You do the same thing here. You compute epsilon CG. You do the same thing here. You compute epsilon FD. So if you do that, then epsilon AH would be 6.981 divided by 200. That's 0.349. The dimension is millimeter over millimeter, or basically it's dimensionless, right? So you can just think of it as being simply dimensionless, which is not a surprise. So strain is a dimensionless parameter. That's epsilon AH. Then epsilon CG is 10.472 divided by 300. That's also 0.349. Again, a dimensionless parameter. And eventually epsilon FD, the last one, is 17.453 divided by 300 millimeters, which is 0.05. Sorry, 0.582. I think I'm consistently missing a 0 everywhere. So those first two digits, I think it's 0.0. It's not 0, just to be clear. All right? Okay. Is there any question? Okay, I also think I was not missing a 0 here. I think I'm actually having 1 0 extra here, right? So this number is almost, let's say it's about 6 divided by 200. No, it's 3 over 100. No, it's correct. Everything is good. All right. Okay, so is that clear? All right, this is the first exercise for today. The second exercise is this one. We have this square in the picture. That is deformed into this shape that you see. Let's say a sort of irregular shape shown by the dashed lines. And the assumption is that this side, it remains horizontal, so they are parallel basically. This angle is given and the dimensions are given here. For this picture, you are asked to compute the shear strains at every corner of this. So here you have a shear strain, here you have one, here you have one, here you have one, and obviously they are related to these angles. Okay? So the first thing I need to remind you is the definition of the shear strain itself. You remember, if we had, let's say, a sharp corner, or if you think of 90-degree angle, and then you have a deformation which changes that, let's say, square into this parallelogram, then this angle here, we call this shear strain. So if this angle was theta, then we define that as pi over 2 minus theta. So let's say for our simplicity here, we assume this sort of convention, meaning that if theta itself is less than 90 degrees, then our shear strain would be positive. If shear strain is negative, it means the angle is larger than 90 degrees. It doesn't really matter too much, as we will see shortly, but this is the idea. Okay, so that's the first thing. The second thing we need to remember is a little, say, geometrical exercise. What we will need in this picture, in this example, is to find a relationship between, let's say, this length and this angle. Okay? In order to do that, I just remind you of something that I'm sure you know, but I think it also helps if I just repeat it here. So let's say you have two vectors, A and B, and these are kind of bold letters, so they are like vectors. And then you are thinking of a vector C in between, like this. Now, if I want to show vector C in terms of A and B, it's going to be B minus A, right? So minus A would be like this. And then let's say B minus A, it's like B plus minus A. So this would be giving you C, right? So that's clear. Now, if this angle is theta, then C squared, or C dot C, would be B minus A dot B minus A, which is B squared, or B dot B, plus A dot A minus 2A dot B. Okay, so this is C dot C. Does that make sense? So what does that mean in this picture for us? If I draw a line here, okay, so that's the line C prime D prime, and let's call this angle theta, then that means for us that C prime D prime squared is C prime B prime squared plus B prime D prime squared minus 2 times B prime C prime times B prime D prime times cosine of the angle between the two, which is cosine theta. Right? Again, maybe you have learned this from your mathematics courses. You didn't exactly do it through vector calculus, but this relationship exists. Okay, so I'm going to remove this, but we would need this basically. We would need this relationship soon because we want to calculate that angle theta. Okay, so that is exactly how we are going to compute angle theta in the next part. Just shift this a little up. Okay. So now that we have this, we have a relationship from which you can compute angle theta, and then if you have angle theta, basically you subtract from pi over 2 or subtract pi over 2 from it, and you get shear strain. The only thing that we need are these. Okay? Now, for C prime D prime itself, you can sort of look from this other triangle also on the left-hand side. So if you look at that triangle, you see also how that thing is calculated. So basically you are having a triangle here. You know, there is this little distance. And then if you add this to that, you get a 90-degree angle, basically. Does that make sense? So if I take this plus that little distance, again, this angle, because it's so small, it's difficult to see, but you can see this. This is what I'm talking about. There is a little difference here, and there is a little difference here. Okay. So between what we would call DD prime, so this is DD prime, but it has two components. It has a vertical component, it has a horizontal component, and then obviously one of them is, is multiplied by cosine of that 1.5 degree, the other one by sine of 1.5 degree. So you will see them coming in our next calculations, but you see why they are coming. Okay, so the first thing we want to do is to compute that C prime D prime. So I'm going to say C prime D prime, or let's say C prime D prime squared, is that a horizontal distance, which is, the horizontal distance from here to that thing, and that has three parts. It has this little part that we just discussed. It has this part, that's the base, and it has this additional part that comes from the deformation. So it's going to be 8 plus 50 plus that little distance here, which would be 53 times sinus of that little angle. So that would be a horizontal part of it. So basically this would be 50 plus 8 plus 53 sine of 1.5 degree squared, that's the horizontal part, and the vertical part of this would be 53 cosine of 1.5 degree again, squared. Does that make sense? So this 53 cosine that angle is basically this height. Okay, so it's just a simple calculation, and from that you can get C prime D prime to be 79.586 millimeters. That's C prime D prime. Then we do B prime C prime. So B prime C prime is this one. And then again, it's a very similar thing. So you need now to look into this triangle. Okay? So if you look into this triangle, you have 8 here, you have 3 here. So this 3 is here. That is the horizontal component. The vertical component is again 53 cosine 1.5. So B prime C prime squared is then again, let's say the horizontal part is 8 plus 3 squared. That plus 53 times cosine 1.5 degree squared. And from that you get B prime C prime to be 54.112 millimeters. Now, the next thing we want to do is B prime D prime. So that's this one. This one is easy. It's basically, taking this and this into account. So it's just a simple summation. So you had, let's say, a base here, then you got this much addition and this much, let's say, subtraction. So that would be 50, that's the base, plus 53 sine 1.5 minus 3. Sorry, this is not a square, this is just B prime D prime. And then B prime D prime is 48.387 millimeters. All right, so now you have C prime D prime, B prime C prime, B prime D prime. You can just insert them here and calculate theta. So we do that, and theta would be 101.73 degrees. Okay, so that's theta. Now, in order to proceed, you also need this, let's say, this other angle at C prime. Let's call it, I don't know, beta, right? So that you also subtract it from 90 degree or pi over 2, and you would say that's shear strain. But that's easy because we know this is horizontal, so beta and theta are both together making 180 degree. So beta is nothing but pi minus theta, let's say in radian. And in terms of degrees, that means beta is 78.27 degrees. Does that make sense? Okay. So now you have all the angles you want. You have beta, you have theta, you have 91 and a half, and obviously whatever is left here, would be the same here. So you also have this other angle here, which I didn't write, but this is going to be 88.5, obviously, right? So we have that. Now, for each of these corners, we can compute the shear strains. So let's calculate shear strains. At corner A, it's 91.5. So gamma at A would be, remember we said it's pi over 2 minus angle in radian. So pi over 180. That gives you a number with a minus because it's, the angle is more than 90 degree. That's gamma A. Gamma B, that's that angle that we just calculated as theta together. It's going to be pi over 2 minus 101.73 degree times pi over 180. That's minus 0.205 radian. Now, what we want to do is to compute gamma C and D. Gamma C, if we use the same calculation, like this XY approach, it's gonna work similarly, but with a different sign. So let's say we just assume it's the way that we did before, but I elaborate on it in a second. So that would be pi over 2. If you are writing it, don't write it. So it would be, if we just use that formula, it would be pi over 2 minus the angle, right? And the angle at C is beta, which is the leftover there. So it's 78.27 degree times pi over 180. So if you do that, you get an angle which looks like this. Okay? So it comes with the opposite sign of what we had up there. All right? This is not a huge surprise because you remember these two angles are making 180 together, right? So it makes sense that at these 2 points, you basically get similar results. The reason we have 2 different signs is that, one of them is more than 90, the other one is less than 90, okay? But if you want to be consistent, you can also, let's say, equally call this, minus like the other one, because remember, we need to look into these 2 angles. Remember we said these are the 2 lines, and then, I don't know, they become like that. Now, if you think of it that way, so if you think, let's say this is y-axis, this is x-axis, right? So now this happens to them. So basically the angle between them is also larger than 90 degrees. Does that make sense? So if you want to have a consistent definition, again, the sign doesn't matter really in this sort of geometrical example. We just want to say it is larger than 90 or less than 90. But you should think about it more that way, that, for instance, if you think about this angle, this is larger than 90 degrees, right? You can think of this is a smaller angle, but then the direction of x and y is flipped. It's shifted, right? Now y is downward. So maybe it makes more sense to actually talk about this angle, which then they give you exact number. So they give you the same sign. Does that make sense? So my point is, do not trust this formula too much. If you do it, you should always think about, the xy coordinate and how we started with defining them. Okay? So if you bring that into account, indeed, you should actually use an opposite definition here, or somehow a definition which is consistent. Okay, so basically what we need to do, or what would make sense more from a mechanics perspective or from our course perspective, would be this, so that you get essentially the same thing. Okay, the same holds for D. So then let me just put this up here. So for D, I'm going to also, I flip the definition basically. So that would be 88.5 times pi over 180 minus pi over 2. And that gives me minus 0.0262 radian. All right, so these are the shear strengths. Yes, so basically we are thinking of a shape that goes from this to this, right? I'm not sure if I understood the question correctly, but that's what you're saying, right? So if you think about that, then these two, they naturally would be identical, right? So that's why these two, they are identical. Use the formula. Yes. Does it make sense? Yeah. So my point is, you may want to think of, if you just think of this example that it becomes this, you may want to think about it like that. Let's say this was like an enlarged version. This is your shear strain. It doesn't matter how you measure it. Okay, this is the same angle. Okay, so, or let me just again maybe I draw a little one here. So if you have a square like this, and then if you say it's going to deform like that, this is your shear strain in this example, okay? So obviously, as I said, this angle is, and this angle both together are 180, but it would have made sense to, you know, if you call this theta and you call this theta prime, it would have made more sense to define it like that, okay? So this would be your gamma. Does that make sense? So, yeah. Because again, you should think of that angle or the change of that angle alone from 90 degree. Any other question? Okay, so this was the second exercise. The third exercise is this one. We have a wire here connecting these two columns, two straight columns, and then after an earthquake, there is a 2-degree angle between the tilted structure and the, let's say, the straight structure. So what happens is basically that, let's say, if I draw it, you have an earthquake, and then this column B would become this. Okay, this would be your column D after the earthquake. This would be your, or that would be the right column. This is the left column. Obviously, I am enlarging it a little too much, but that little angle is 2 degrees. And under this condition, you are asked to compute the strain in this cable. Okay, determine the normal strain in that cable. So basically what happens is you need to compute the length of that cable after the formation and before the formation. So after this earthquake, point A would jump to this point. So let's call it A prime, right? Point B would jump to this point. Let's call this B prime. So there is A prime there, there's B prime there, and then there is this, let's say the new cable itself, okay, or the new wire. That is A prime, B prime, okay? So if you have the length of A prime, B prime, so A prime, B prime minus AB divided by the length of AB, that would be the strain that, or the epsilon that we are looking for. Now, AB itself is 5. It's easy to see that. So AB is the length here. The horizontal part is 4. The vertical part is 3. So that's 5. This is our usual triangle. So AB is 5. All you need to compute is just A prime, B prime then. Now, how do you do that? It's a simple exercise compared to what we had previously. You just think about this triangle. You would have, let's say, the X, the Y coordinate, and A prime, B prime can be obtained from there. So you would say A prime, B prime is, or let's say A prime, B prime squared is 3 to the power 2. That's the height, right? So this height is 3 plus the horizontal part is this. Okay? So what is this? This horizontal part, which let's call it X, this x is essentially your initial 4 plus b prime minus a prime. Does that make sense? It's just they are in one direction, right? So I'm going to call this x squared. And as I said, x is nothing but 4 plus bb prime minus a prime. Now, bb prime is height times tangent of that little angle, theta. But then again, this angle is much less than, let's say, pi over 2, so we can assume that that tangent is the same as the angle itself. So bb prime would be this height, which is 4 times the angle itself, theta. So bb prime would be 4 times theta, and theta is 2 degrees. So that's 4 times 2 divided by, 2 times pi divided by 180. So that would be 0.1396 meters. A prime, on the other hand, it would be just 1 times theta, because that little height is just 1. So that would be 1 times 2 times pi over 180, which is 0.0349. Okay, now you have your a prime, you have bb prime. So you can just calculate x from that. X would be 4.1047 meters. Okay? Now you insert that into this equation, you get a prime b prime. So you do it there, and then a prime b prime would be, let's say, a square root of 3 squared plus 4.1047 squared. So a prime b prime is 5.0842 meters. Okay? Now you have a prime b prime that we wanted to have. You just subtract 5 from that, you divide it by 5, and you calculate epsilon AB from that, which is 0.0168. And then again, it's dimensionless, or you can think it's meter per meter. Does that make sense? All right. That's the third exercise. The fourth and the last exercise is this. You have a rubber band here between B and A that is 1 meter at the beginning. And then let's say you have some shape here with the surface being, let's say, a quadratic polynomial. You stretch that rubber band such that it gets nicely attached to that surface. Okay, so this thing becomes this. Now, obviously, the length of BA prime, so the deformed rubber band, is longer than the original one. And by doing that, we introduce some strain in it. Okay, so this question basically asks you to calculate that strain. So epsilon that we want to calculate is the final length, it's BA prime, minus initial length, BA, which was, by the way, 1, divided by the initial length, BA, also 1. Okay? So that average strain just happens to be BA prime minus 1. So all you need to do is to compute the length of BA prime. Now, how do you do that? If you remember from your mathematics, if you think of a little piece here, it has dy and it has dx. Okay, so the length BA prime is an integral from B to A prime of dx squared at every point plus dy squared, right? Now, sorry, square root of that. Okay? So that basically means you can say it's integral from 0 to 1 of square root of 1 plus dy over dx squared, dx. Now this is your common integral. This is something you can do. And here, dy over dx is nothing but, y is x squared, so dy over dx is simply 2x. So this integral is simply integral from 0 to 1, square root of 1 plus 4x squared dx. So you can just integrate it using the formulas that you know better than I do, or you can use your calculator. You get something like 1.4789 meters. All right? So that's your final length. You subtract 1 from it, and you get your strain. So epsilon would be 0.4789. Again, dimensionless. Let's say this is about 50%. Okay. This is very important. You see, this is huge. The strain of 50% is very, very large. We don't have this sort of strain in usual mechanics, okay? Think about it this way. 100% strain means 2 times as large. So if you make something 2 times as large, it's 100%. Okay? So this is very large. But in this particular question, it tells you that we are talking about a rubber band. So, rubber band is very soft and elastic. So that kind of works. But for our usual engineering question, you usually have 2 zeros before seeing any number here, So be aware of that. Do you have any question? All right, this was the last exercise for this recitation.